Thanks a lot, Jonathan, in particular, from the perspective of our CEOS Systems Engineering Office. We can hand over to you for a brief background and primer on our CEOS Analytics Lab. Thank you very much.
Thanks, Dave. Today I'll talk a little bit about the CEOS Analytics Laboratory called CAL, and a little bit about, I'll touch a little bit of technical detail about what it is, perhaps why it's a little bit different, what we can do with it, and try and give a bit of a general introduction of where we're up to. But essentially, there's a little bit of information on the CAL website at cal.ceos.org. So on this site, there's access to the system for those who have got accounts, but you can also request an account. There's a data request form as well for people that are interested in different data sets being added into the system. And there's a support request for users as well. On the website, you'll also find a white paper that talks a little bit about the system. But today I'll talk a bit about what is CAL, how it fits together, a little bit of technical detail, but what you can do with CAL as well. I'll talk a little bit about some of the detail of some of the capabilities around parallelization and multitasking within CAL, and some of those advanced capabilities linking into things like graphics processing units and things like that, and finish off a little bit of a summary on the system. Initially, I want to start with a bit of a technical, almost architectural overview around how CAL works, how this all fits together. Initially, there's lots of data that's being processed out there in the outside world, sitting in different public cloud systems, not only AWS, but there's also data that's been processed, obviously, by US government agencies, USGS and NASA, but also Europe, the European Space Agency, and a whole heap of others that put data into systems like the AWS Open Data Registry. There's similar, of course, data going out into Google platforms, Microsoft platforms, etc. But we take or we connect to and make use of the data that's sitting in AWS. Now, the benefit of this data is that it's already been converted into the formats that we can make use of. So the key thing with cloud data systems is that we want to use what's now called analysis-ready cloud-optimized data formats. This is primarily COGS, cloud-optimized GeoTIFFs, and ZAR, which is a multi-dimensional file-based data format. So there's a lot of this data sitting out already, processed into these formats in AWS, along with some key metadata information. So we can connect the data sets that have either EO3 metadata or stack metadata records. And essentially the way that CAL works is that we connect we connect to that information by storing an index of that data in a database service. We use the Amazon RDS, relational database system, and basically that lets us keep an index of data that's already out in the public domain. That means we don't have to move the data, we don't have to copy the data, we can use the data in situ, and we just move the compute to that data. So the way we do that is that we have a scalable computing environment using Jupyter Hub. The default system has 32 gig of RAM and 8 CPUs, and a whole heap of other capabilities. But essentially users, through tools like the Open Data Cube, can ask questions of that data. So they can go and look for data in a particular part of the world for particular dates, load particular bands of different satellites, and that data is delivered back into the Jupyter environment for processing. But we also connect to that the capabilities of what's called a Dask cluster, and this is a scalable cluster that you can connect to your Jupyter environment to do much more advanced processing. And I'll talk a little bit about that in a few slides. On top of that, though, we have the ability to turn on web services. So we can connect to the same data. We can connect OGC WMS services, so web mapping services, web map tile services, or coverage services. We can connect those systems to the same data stores, again, without moving the data, and connect that into visualization tools. So we can use tools like Terrier, or these, of course, OGC, which are standards compliant services, can connect into lots of other visualization tools as well. But in addition to that, we have a third main component called Argo, which is a workflow environment, a workflow engine that lets us take pieces of code that might process data. So it might be a piece of code that talks to the Snap processing environment for radar data, for Sentinel-1 data or others, and goes and converts that into the cloud optimized formats that we need. Or it might simply be taking some NetCDF data and converting it into COGS or into ZAR. Now, the net result of that is that we can use this system to produce new data. And instead of putting it in public buckets, we can put it in some of our own areas within Amazon, within AWS, in our own buckets. And effectively, that means that we have the best of both worlds. We have access to all of the public data, but we can also process our own data to create new products or integrate new data sets, store it in our own buckets, and flow through the whole process again. So we can index that data within the database and then connect it into the Jupyter environment for analysis, or into web services. So that makes the system very powerful. We're not limited to just using the data that's already out there, and we can run workflows that are very, very large and process very large areas, continental scale processing and analysis to produce new products from different satellite or other gridded data sets. All of this makes use of a whole collection of technologies, lots of different parts of AWS, but fundamentally this is powered by the Open Data Cube software, which is open source. But around that, all of these other components are based on, or we used CSIRO's Earth Analytics Science and Innovation platform, which brings all of these other components around Open Data Cube. So if anyone's interested at any point, happy to talk in detail about any of these technology components, but I'll skip over the detail of those today. So what does that give us? As we know, satellites are out there collecting time series of data. All of this data is building up in data stores and archives, and we can process that not only into what used to be called analysis-ready data, ARD, but now into analysis-ready cloud-optimized data. So that lets us create big stacks of the public data, or connect to the big stacks of public data like Landsat or Sentinel-2, but also we can process Sentinel-1, Sentinel-3, and lots of other satellites. We've got existing workflows for MODIS, VIIRS, ALOS, DEMs, elevation data. We're working on small sat processing and commercial satellite processing. So that gives us a lot of flexibility to put lots of different data from lots of different sources together and connect that into these systems. So this is then where we can either just do simple visualizations, exploratory analysis, or really custom things and develop new products and new systems. And that lets us go from a pilot scale. A user in the system working in Jupyter can work at very small scale and just look at 1 year of data or a small pilot area, and then scale it up to continental scale. And to do that, we can use a single computer, or we can scale up to use 200 or 1,000 computers. So that is what lets us move from very small scale to national or continental scale. We've already got quite a bit of data in the system. In the website explorer.cal.ceos.org, this is a website or a web application that comes with, as part of the Open Data Cube ecosystem. Basically, it's a metadata viewer that lets users look at where do we have data, what variables, what parameters, what dates exist for different products. But essentially, we've got coverage in all of the contiguous US plus Canada, plus areas in South America, some project areas in Europe, Bay of Bengal, etc., for all of Landsat, both surface reflectance and surface temperature, different elevation products, a collection of Sentinel-1 data, the same coverage for Sentinel-2 for the whole history of Sentinel-2. And then we've got some Pulsar-2 data as well, and we can process more. When a user comes in and accesses the system, essentially they've got an interface where they can choose the workspace that they want to work in, essentially the project that they might be working on at the moment. They can choose the number of CPU cores, choose the amount of RAM that they want for the analysis that they're going to be doing. They can choose a particular environment. For most users, they just use the default environment, but we've got a number of different environments with different machine learning capabilities, etc., and the version of the system. Users can go and use the latest cutting edge development version or the latest stable version, or they might want to go back to an old version of Python if they'd developed something a year ago and need something that's more compatible with their code when they wrote it. All of that's very flexible, and users can start different systems depending on their needs. When a user is in the system, they've got access to, it's between around 500 and 600 different Python libraries. Fundamentally, this is a Python-based system. Lots of that relate to visualization tools. So there's a whole collection of visualization tools. But one of the most important pieces is a library called Dask. And Dask is what lets us take code and parallelize code. Rather than having a very sequential, slow analysis system, Dask goes and takes all of that and splits it up and lets us run code in a more parallel sense. And I'll talk a little bit more about that next. So, as I said, Dask is what enables parallelization. The default machine that a user starts with has 8 cores and 32 gig of RAM. And there's 2 options to scale up. One is to go and use a bigger machine. We can give users access to machines with 64 or 128 cores and 256 gig or 512 gig of RAM. But that sometimes is actually quite limiting. The other way to do it is to connect your notebook to a remote cluster. Essentially, a cluster is a collection of additional machines, additional workers that could just be 2 or 5 or 10 machines, or it could be 100 machines. Each machine generally has 8 cores and 32 gig of RAM, but that's configurable. You can even set up a cluster of GPU machines if you're doing some really serious machine learning work. So this gives a couple of different ways to scale and do flexible things. For some uses, things like processing radar data, you might actually need a big machine with a lot of RAM, but both of these options exist. So Dask essentially starts with the client, which is your notebook. You write your code, but then when you start a cluster, you essentially have access to this collection of connected workers. I'll talk a little bit more about what the workers are in a second. But if we look at one really simple example, if we take 2 functions, for example, the first function is just going to increment a value by 1. It will add 1 to the variable that's passed into it. And a second function is going to add 2 variables together and return the result. In this example, if we start with x as 1, we run the increment function to increment the value of 1 by 1, that returns 2. And then we're going to add the 10 to the value of y, which is 2, and ultimately z will be 12. So that's a fairly linear process. And Dask sees that like this. Dask creates what are called task graphs. And essentially what this does is to say, well, to arrive at z, we need to run the add function, and we need to have the inputs of 10 and y. To get to y, we need to run the increment function, and that needs the input of x. Now that gives us something that can be split up amongst workers. Here, this is very simple. We've got 2 jobs to do, and those are fairly linear. But if we want to do this for every value of x from 1 to 10, that's a very simple parallelizable problem. Now, normally the way we might do that in coding, particularly in scientific coding, is just put that in a loop, and we'll say for 1 to 10, go and run this function. But that's very linear. That doesn't actually save us any time. We have to run that sequentially. But what Dask can do, if we set it up the right way, essentially we say, go and calculate this result for every value of 1 to 10 and do it all in parallel. And that results in really complex task graphs where you've got lots of inputs, lots of processes, lots of things crossing over, and ultimately coming together at one point. But Dask handles all of this, and it works out how to go and schedule all of these tasks. And you don't have to worry about it too much. It happens in the background. But there is a bit of a change in coding and scientific programming to go from the process of using a very top-down for loop or something like that to something that actually uses Dask in the right way. So that's a little bit of a learning curve, but we can help with that. So you can set up to handle this either a local cluster or a remote cluster. A local cluster essentially takes your existing machine and chops it up into workers to do this analysis. So if your machine has 8 cores and 32 gig of RAM, and you just say, create a local cluster, it's going to chop that up into 4 workers and is going to be able to parallelize that work. And you get a little dashboard that shows you that you've currently got a client with a local cluster. There are 4 workers. There's a total of 8 cores. In this example, there's 24 gig of RAM. And each worker, there will be 4 workers. Each worker will have 2 cores and 6 gig of RAM. And that gives you a pool of workers to do your analysis. You can do the same thing with a remote cluster where you might have additional machines. It looks the same, it works the same, and that's what makes it easy to move from working on a single machine to working on 100 machines. You don't have to change anything. You just turn on a remote cluster and you start working in the same way. The message here is that you should always use at least a local cluster. This helps your code work much more efficiently and helps divide the work up and parallelize the code. So the net result is that you end up loading some data, and this is what loading Earth observation data in Dask looks like. You end up with an X-array object, and fundamentally Cal and Open Data Cube systems work with X-array. And in this example, we've loaded 43 times and a small area of 403 pixels in the Y direction by 342 pixels in the X direction. And this is probably Sentinel-2 or Landsat or something like that. And here we've loaded 3 bands, the blue, the green, and the red band. So a very simple example. But the important thing to note here is that the data type we've loaded is actually a Dask array. So this is a Dask array inside an X-array object. And what that means is that we've got this object inside by expanding the blue variable by clicking on the little database icon. We can see what is in here. And we've got about 11 megabytes or megabytes of data broken up into 43 chunks. Each chunk is essentially one date. So we've got a data cube loaded with a whole heap of slices of data. But the important thing here is that Dask loads this as a future. This is just a promise to load the data when you need to do something with it. And essentially the chunks, you can think about this as in the context of satellite data. Essentially, it's chopped up into clusters of pixels. In this example, we've got a single chunk for a whole scene, but we can also chop this up into smaller pieces. We can, when we choose to, we can actually convert this from Dask arrays into real NumPy arrays, into real values. We use a function called compute to do this. And this is what then converts it into from working in a Dask array actually to working in real numbers. And the power of this is we can choose when to do this. We can, in this example, we're just loading some data. But in a more complex example, we may have done some calculations, we may have done some cloud filtering, produce some indices, or something much more complex. We can delay that compute step until we've built this process, this workflow. And when we're ready, we then actually say, now we want to go and do the compute, and Dask will work out how to marshal and schedule all of those jobs and allocate those across your compute capacity in your cluster. So that makes this very, very flexible. It means that we can step up to examples like this, where we might have 10,000 pixels by 10,000 pixels and 450 dates. And in this example, there's 180 gigabytes of data loaded into this Dask array. Now, this would be possible to do on a 30 gigabyte machine, but it's impossible to load that into real memory. So this is a way where we can work with very large amounts of data and then go and calculate a derived product that might only be megabytes in size, but we're accessing gigabytes or even terabytes of data to come up with that product. In the end, that gives us a very parallelized process where Dask goes and works out how to compute the final product. And there's a range of dashboards, etc., that you can look at when you're running these processes to understand what's happening, track performance, look at all of these tasks running in parallel, etc. But there's other presentations we can give that talk a lot more in detail about Dask. On top of that, Cal has a whole heap of other advanced capabilities. As I mentioned before, we can enable GPU nodes. So this opens up a whole world of machine learning and AI processing. There is an R environment that we can enable. It's not as connected to things like Open Data Cube as the Jupyter environment, but it's there if people want to use it. Lots of machine learning libraries, lots of other Python libraries and advanced processing libraries that are already in the system. And we update these images generally every quarter. So we try to keep up to date with the latest Python versions of all of these packages. We've also got a collection of example notebooks and training materials that people can use to start to get to know the system. Various things like classic things like calculating cloud statistics and filtering, looking at changes or looking at water, vegetation, a range of spectral examples, SAR examples, etc. So there's these not only in our own notebooks, but also because this is built on the Open Data Cube, there's lots of other examples out there, and there's a community working with ODC, with the Open Data Cube that you can make use of. Who's using Cal at the moment and who can. So this is open to all of the CEOS working groups, virtual constellations, and other groups connected with CEOS. We've been working a lot with Coast and Biodiversity, including developing training sessions and materials, but this is all actively in development. So we can definitely look at adding new data or new capabilities to suit the needs of different users. And therefore, the team, myself, and also the team at AMA are available to look at what data might be needed, what new products, what sort of training, are there additional Python packages that are needed, and how can we help look at analyses of different scales. And just to finish off, so really Cal is a very flexible environment. There's lots of other examples out there from systems like Digital Earth Australia, Digital Earth Africa, that don't take too much to copy across into Cal and modify. There's always differences in Python libraries, etc. But it's pretty easy to take a lot of these examples from big systems around the world and adapt those for use in Cal. And chances are, anything that you're wanting to do, there's probably examples that we can take and modify and adapt. There is going to be a little bit of a learning curve if you haven't used things like Dask before, but the team's available to help out. So that's a very quick overview of Cal. In terms of points of contact, Dave Borges, myself, or Brian Terry in AMA, and you're more than welcome to get in touch.
Thanks very much, Jonathan. Really appreciate that brief background and explainer on our CEOS Analytics Lab. And yeah, I'd reinforce if anybody does have any questions, please reach out to our CEOS Systems Engineering Office team.